All right, our next section is going to be 6.6 exponential and logarithmic functions. Today we're going to take a look at starting to solve exponential and log functions using one another as inverses, where we can't solve them necessarily with equality properties as we have before. So just a quick reminder that exponential functions are one-to-one. So if I have an exponential function that meets the definition, meaning I have a positive base, so on and so forth, the following conditions are true for x1 and x2. If x1 does not equal x2, then b to the x sub 1 does not equal b to the x sub 2, assuming I have the same base on each side of my equation. However, if I have the same base, b to the x sub 1 equals b to the x sub 2, then the only way that this is true is when x1 equals x2. All right. So what we've got then is that if I know that I have two equal quantities and my bases were the same, the only way that's true is if my exponents equal one another. All right, we're going to use this one a good bit. This is one that that you should have seen before, right? But this one, the exponential equality property, we will use a good bit. All right, this one can save us a lot of extra work. Pardon me. A lot of extra work with other types of solving methods if we can check this one and do this one first. Okay, so general guidelines for solving exponential equations. All right, so first things first. All right, we're going to attempt to solve and rewrite each base using the same number. It's not always going to work this way. Okay, the first thing you should always try is to rewrite using the same base. Once you've done that, if it's possible, set the exponents equal to one another using the condition above, all right? And then go ahead and solve whatever you have left. Typically, it'll be a linear function, okay? If that doesn't work, then from the original equation, like if you look at it and you have a 4 and you have a 9 as your bases, you're not going to be able to write them with the same base. So you're going to have to take a log of both sides and then use our log properties to solve it, and we're going to look at that here in a minute. Okay, so let's look at some same base examples real quick. So here on the very far left, I have 7 to the x plus 6 equals 7 to the 3x minus 4. My bases are the same, therefore I can set my exponents equal to one another. So we're going to end up with x plus 6 equals 3x minus 4. And if I go to solve, if I subtract 3x on each side, I get a negative 2x equals a negative 10 when I subtract 6, or x equals positive 5. In my second example, I have a base 3 and a base 9, 3 to the 5x minus 8, and 9 to the x plus 2 power. Right? I'm going to rewrite this using a base 3 on both sides. So 3 to the 5x minus 8 equals, and you would agree that 9 is 3 squared. So when I have 3 squared to the x plus 2 power, remember that I distribute or multiply when I have a power raised to a power. So when I distribute here to that entire exponent, we're going to have 3 to the 2x plus 4 power. Don't forget to multiply completely and distribute. All right. So again, now I have like bases. I can set those exponents equal. So we're going to have 5x minus 8 equals 2x plus 4. I'll subtract over the 2x. I get 3x equals, I'm going to add the 8, 12, or x equals 4. In my last example that I have here, I have 27 to the x minus 1 equals 9 to the 2x minus 3. Note that I can rewrite each of these using base 3. 27 is 3 cubed, and 9 is, as we just saw, 3 squared. So when I rewrite this, I'm going to have 3 when I distribute to the 3x minus 3 power equals 3 to the 4x minus 6 power. Again, now I have like bases. I can set my exponents equal to one another. We're going to have 3x minus 3 equals 4x minus 6. When I subtract over the 4x, I'm going to get a negative x equals a negative 3, or x equals 3. Right? So again, I could have solved these by taking the log on both sides. However, it's going to be a lot more work than what I just did here, right? When we have exponential functions, the simplest, easiest way to solve them is almost always going to be with like bases if it is possible. So let's take a look at what happens when I can't solve with like bases. So here I have a 3 to the x equals 5. There's no way with integer values or anything that's reasonable that I can rewrite these using the same base. So my only option is I got to take a log of both sides. At the end of the day, it does not matter what log I take. I can take any log and the log properties work. Okay, so I'm going to show you this problem 2 different ways. There's an intuitive log that you might say, well, let's take that. Okay, and that would be log base 3, because my only exponential here is a 3 to the x. So if I take a log base 3 of both sides, and again, I want my exponential isolated before I do that, if that needs to happen. Okay, log base 3 and the 3 to the base of 3 cancel, and I'm left with x equals log base 3 of 5. Now, if you remember back, I had said earlier that the only log you're allowed to have in a final answer, you can have a log base 3 throughout the problem, but the only type of log for a final answer has to either be a common log or a natural log. So here I need to use my change of base formula to rewrite this either into the natural log or the log base 10, right? And remember, the change of base is the log base b of x equals the log of the quantity over the log of the original base, or the natural log of the quantity over the natural log of the original base. And again, I can write it in any base that I want, but here the only 2 that make sense to do it are the 2 for final answer. So here I get, let's say, the natural log of 5 over the natural log of 3. Okay. Now the other way I could have done this problem, right? So let's assume I still have my 3 to the x equals 5, right? So I'm going to do this the second way, right? So the other thing I can do is I can take a natural log of both sides right here. And once I've now taken that natural log, I can use my power rule to bring this exponent down in front. So I get x natural log of 3 equals natural log of 5. Natural log of 3 and natural log of 5 are nothing more than real numbers. So this is, for all intents and purposes, just like having 3x equals 5, where I'm going to divide by 3 on both sides. Instead here, now I'm going to divide by a number that's natural log of 3, and it's going to be irrational. So when I divide both sides by the natural log of 3, I get natural log of 5 over natural log of 3. Hey, what do you know? We get the exact same answer. Okay? So by all means, either way works. When you have something really simple like the equation that we're dealing with here, taking the log base 3, because that's the intuitive base for this problem, might actually be easier to do that and then change the base at the end. When we start getting to problems where I'm taking a log on both sides, where I'm bringing exponents down, and especially where I have a different base on each side, and I have to bring exponents down where there are multiple terms in that exponent and I have to distribute, if you then have to do multiple change of bases at the end of that problem, it's going to be nightmarish. Okay, and I really caution you against taking what I'll say again is the intuitive base, and I would encourage you to either take the natural log or the log base 10. All right, so let's take a look at another problem here. So here I've got this. All right, this is a log expression that we should be able to evaluate by hand. All right, so here I have log base 6 of 64 equals log base 6 of 4. So you might be saying, well, I don't know what the heck the log base 6 of 64 is. Okay, and maybe you could change the base in the numerator, you could change the base in the denominator, and maybe you come back to something, but at the same time, you end up with a complex fraction, and there's something crazy that'll happen there that's not really going to work very well for us. So I don't actually want to do that. All right, notice that I have the same base in both my numerator and denominator. Remember my change of base formula from above. Okay, I can change any log into a different log using the same base in my numerator and denominator. Remember I said I had the log base b of x equals, and if I say log base A of x over log base A of the original base B, well here, A is that base 6. My original quantity was 64. My original base was 4. So I can rewrite this, and really when I do that, when I do this next step, that log base of 6, the 6 is going to go away, and I'm left with log base 4 of 64. And I ask myself, 4 to the what power equals 64? And it's going to be 3. Okay? So there were a couple of different ways we could have simplified this, but once in a while, and I know our book does it to us, and I think on one of the tester quizzes, you're probably going to see something like this, where you're going to have something written, whether it's standalone by itself, whether it's thrown into a problem somewhere that you have to do change of base backwards to get back to something that then is simplifiable. So if you have a fraction or a ratio of logs with the same base, and it's something that you're like, man, I can't evaluate either the numerator or the denominator, take a look and ask yourself, if you did change a base backwards, based on the quantities that you have here in your inside of both of your logs in the numerator and the denominator, could you take a log if it was the base of that quantity? All right. To take a look at it, it's possible that may be what you need to do. Okay. So again, change base formula, I have it here because of that problem, even though we already talked about it above. So I'm going to keep moving. All right. So let's take a look at solving some log equations, and we did some of these yesterday. So here I've got log of x minus 5 minus log of 2x minus 6 equal to log of 1 over x. So again, I need to condense this to a single log on each side. On the left-hand side, I'm going to use the quotient rule, and we're going to write this as the log of x minus 5 over 2x minus 6 equals the log of 1 over x. Now again, log equality property, I have a single log on each side. The bases are both 10. I can set my quantities equal to one another. So I can set x minus 5 over 2x minus 6 equal to 1 over x. And what I want to do at this point now is I'm going to cross multiply, right? I've got a proportion to solve. So here, when I cross multiply, and I'm going to distribute just for the sake of time, we're going to have x squared minus 5x equals 2x minus 6. Here I've got a quadratic that I need to solve now. So I'm going to get everything on one side of my equation. So we're going to have x squared minus 5x, all right, minus 7x, okay, and plus 6 equal to 0. And then I ask what numbers are going to multiply to positive 6 and add to negative 7. They're going to be x minus 7, or sorry, x minus 6 and x minus 1. Okay. When I solve these, then we're going to get x equal to 6 and x equal to 1. Now, the one thing I need to do, okay, remember, logs have domain restrictions. I need to check to make sure that I don't have any answers that need to be marked as extraneous. So when I plug these back in, what I'm really looking for is, in my original equation, in any of these log quantities, do I get a negative when I simplify it? And I'm looking specifically, in this case, at the 1. When I plug the 1 into either the log of x minus 5 or the log of 2x minus 6, I'm going to get a negative quantity, right? I'm going to get the log of negative 4 or the log of negative, actually, 4, okay? Pardon me, all right? I am not allowed to take the log of a negative number. This is extraneous. I want you to put an x through the equal sign, write ext underneath. All right, the 6 is going to check out. All right, I do not want you to erase that x equals 1, right? Leave it there, all right, because you should have found it, okay? But you should have also then found that it was extraneous. So don't get rid of it. Leave it there. Just put an x through the equal sign, put an ext underneath for extraneous. Again, remember, logs are 1 to 1, okay, by themselves. It is possible we get two valid solutions in a log equation. More often than not, though, if we have two solutions, one of them is probably going to be extraneous. So we need to be very cognizant of that and check it. All right. And check both. If you found that one was extraneous, don't assume then the other one has to work. They could both be extraneous. Okay. All right, let's move on here. So the next one that I come to is 3 to the 3x plus 2 equals 7 to the 2x plus 1. Now, this is where I was talking about I could take the intuitive log on one side, like a log base 3 or a log base 7. Yes, it'll get rid of the log on that side, but I have some messiness on the other side. I'm still going to have to use log properties and distribute, and now I'm going to have multiple places in my equation where I'm going to have to change the base at the end. No matter how I do this, this is going to get messy. Okay? Trust me on this one and use the natural log or the log base 10. I'm going to use the natural log simply because it's one less character and it's going to save me a little bit of writing. Plus, I don't know, I have a thing for the natural log over log base 10 because it works nicely in a lot of other applications as well. Okay, so I'm going to take a natural log of both sides here. So when I do that, we're going to have a natural log of 3 to the 3x plus 2 equals the natural log of 7 to the 2x plus 1 power. And again, now that I've done that, all right, now I'm going to be able to bring my entire exponents down as coefficients. Now remember, I'm bringing the entire exponent down times that log. Even though it's not in parentheses up top, you need parentheses because you're going to have to distribute that entire that log to the entire exponent. Okay, so once I've done that, now what I can do then, right, is I'm going to distribute the natural log on each side into that set of parentheses. So what I'm going to get here is a 3x natural log of 3 plus 2 natural log of 3 equals 2x natural log of 7 plus 1 natural log of 7. Now I've got natural logs of 3, I've got natural logs of 7. I can't necessarily combine like terms here, okay? And not really can't necessarily, I can't. All right, so what I need to do is identify all the things that have an x in them, right? Anything with an x in it, I need to get on one side of the equation. Everything else I want to put on the other side. All right, so I'm going to do a little rearranging here. I'm going to end up with a 3x natural log of 3 minus a 2x natural log of 7 equal to a natural log of 7 minus a 2 natural log of 3. Okay? So what I've done is everything with an x in it is now on this side of the equation. Everything that does not contain an x is on the right-hand side. X is the greatest common factor. I want to factor it out on the left, okay? Because I can't combine like terms. The only thing I can do here is a GCF. So when I pull that GCF out, we're going to have x times 3 natural log of 3 minus 2 natural log of 7 equal to natural log of 7 minus 2 natural log of 3. And I'm going to now divide, just like before I said when I had x natural log of 3 equals natural log of 5. It was nothing more than, it was fundamentally the same as 3x equals 5, you divide by 3. Here, now I've got a number times x equals another number. I'm going to divide by that number. In this case, it's going to be messier, it's going to be bigger, and I'm going to have natural log of 7 minus 2 natural log of 3, all divided by 3 natural log of 3 minus 2 natural log of 7. This is a final answer. Stop. Okay? Let me do one or two things here real quick. I'm going to make a copy of this real quick and put it over here so I can mess with it a little more. All right? This is a final answer. Okay? I want you to stop here. Now, if you were putting this into a calculator, you need parentheses around the entire numerator and the entire denominator. I cannot stress that enough. If you don't put parentheses here, the calculator will interpret this incorrectly and you will get a wrong decimal. A lot of times I'm going to ask for the exact answer, so you're going to leave it in this form. But if I did ask for a decimal, not the exact answer, and you have to type it in the calculator, you need to know how to type it in correctly. Okay. I always say, please make sure as soon as you get to a final answer, stop. Right. This is one of the places where you can keep going. I don't want you to. Okay. Here I have x equals a quantity, and that quantity contains no more x's, so it's solved properly. all of those things on the right hand side are either in log base 10 or natural logs. Okay, they're in an acceptable form. Could I use power rule, quotient rules, and condense this and simplify this? Absolutely. Okay, but if you get to this point correctly and you continue on and you make a mistake, I'm going to mark it wrong. I'm going to take off a point for it. Okay, so as soon as you get to a final answer, stop. All right, like I said, here I could go farther with it. I could bring this 2 up, right? And I would have minus natural log of 3 squared, or 9, over natural log of 27 when I bring the 3 up, minus natural log of 49. And then I could use quotient rule and write this in my numerator as natural log of 7/9 over natural log of 27 49ths. And really, I could use change of base and work backwards, okay? And I could write this as a final answer as the natural log, or sorry, the log base 27 49ths of the quantity 7/9. Any of these, unless I did some silly math, if you type them into the calculator, are going to give you the same decimal approximation. Again, when you get to a final answer, stop. Okay, I had a student years ago who was, well, a little over the top, shall we say, in terms of some of the things. He would solve every quadratic with completing the square instead of some other easier methods for problems. For these problems, he insisted that he was going to completely simplify it because he just didn't like the fact that it wasn't simplified all the way and you could simplify it more. He missed 2 problems for the entire year, and one of them was a problem like this because he did a silly mistake after he had a correct final answer. Okay? Don't be like him. Okay? Get to the final answer, put a box around that thing, move on. All right? If you have questions about what I did there, let me know in class. We can talk about it more. I can show you some of the other things. And at times there might be some merit to simplifying farther. For our purpose here, I don't want you to do that. All right? Next equation. I have e to the 2x equals 4e to the x minus 32. Remember back to quadratic equations, right? And we did quadratic form equations. This is a quadratic form equation. All right. So here, think about it. What quantity times itself gives me e to the 2x? It's e to the x. Well, I have an e to the 2x. My middle term is e to the x. Okay. Just like quadratic form, if I had x to the 6th and a middle term of x cubed, I had a quadratic form. I've got the same thing here. Okay. I could let u equal e to the x. If I do that, I'm going to have u squared plus 4u minus 32 equal to 0. And then I can go through and solve. 2 numbers that multiply to negative 32 and add to 4 are going to be u plus 8 and u minus 4. For solutions of u equals negative 8 and u equals 4. Okay, let me work on the other way to do this, and then I'll catch up, and because we'll be at the same place then. Okay, if I solve this straight up without doing the u substitution. Okay, so if I said, well, I'm just going to factor it right away, so this would be e to the x plus 8 times e to the x minus 4 equal to 0. If I said each factor equal to 0, I have e to the x plus 8 equals 0, and e to the x minus 4 equal to 0. When I go to solve, right, I'm going to have e to the x equals negative 8, and e to the x equals 4. Now over here on the right, at this point I had u equals the 2 quantities. I have to do the backwards substitution and write, oh, it keeps changing to eraser. E to the x equals negative 8, and e to the x equals 4. So I'm at the same place here at this point now. Right? If I go to solve, right, I would take a natural log of both sides because I have e to the x's. So So if I take a natural log of both sides, let me do this here. Well, I don't want to do it there. If I just do the natural log, right? So I'm going to have x equals the natural log of -8, and x equals the natural log of 4. Notice this is a problem. I can't take any log of a negative quantity. Okay. Also think about it from this point here. An exponential function, unless it's shifted, is never going to equal a negative value. So really at this point I could have said I've got a no solution for this particular part. So my only solution here is going to be that natural log of 4. Okay. There we go. All right, so same thing, right? There's a no solution for that one. Here we're going to get x equals the natural log of 4. Okay, no matter how I do this problem, we still end up getting the exact same answer. Really a matter of preference whether you want to do the u substitution or whether you want to factor it straight away. Okay, if you do the u substitution, make sure you back substitute. Okay, if you give me answers of u equals -8 and u equals 4, you're probably losing 2.5 points depending on how many, if it's out of 4 or 5 points. Okay, so again, 2 different ways you can do this problem, either work. The last example that we're going to do here today, all right, is this one. I have e to the x minus 4e to the negative x equals -3. So I've got some negative exponents in here. Think about what a negative exponent does, right? Remember, if I have, say, x to the negative nth, this is 1 over x to the n. So what I have here with that 4, or not minus 4e to the negative x, what I really have is e to the x minus 4 over e to the x equals -3. Now think about something else we've done before as well. This now kind of falls into, not entirely, but kind of falls into those rational equation types. So what I want to do is I want to figure out what my least common multiple of my denominators is, and I want to multiply through so I clear it, right? So in this case, the least common multiple of my denominators is going to be e to the x. I want to multiply both sides of my equation by e to the x. When I do that, I'm going to get an e to the 2x minus 4, because the e to the x or e to the x cancels, equals -3e to the x. I've got another one of those quadratic-like or quadratic form equations involving e here. So here I got e to the 2x plus 3e to the x minus 4 equals 0. And if I go to factor this, I'm going to end up with e to the x. Let's do plus 4 times e to the x minus 1 equals 0. I'm going to come up over here. We're going to have e to the x plus 4 equals 0, and e to the x minus 1 equals 0. Or we get e to the x equals -4, and e to the x equals 1. All right, e to the x equals -4. There's no solution there. It's never going to happen. Okay. Here, e to the x equals 1. There's two ways I can simplify this. All right. I can either take the natural log of both sides, right, which is going to give me x equals the natural log of 1. Okay, probably the most intuitive way. Hopefully from here you realize the natural log of 1 has to be something. Okay, so anything to the what power, in this case base e to the what power equals 1, right? In this case x is 0. Okay, I could have also picked that up from here. E to the x equals e to the 0, or x equals 0, right? Since I had the 1 there. If you didn't notice it that way, that's fine. But one way or another, your answer here is going to be x equals 0. Okay? So what we did this morning or today is a bunch of different types of equations, a bunch of different ways to solve things and things to look out for. I probably haven't covered every single type of equation that you may or may not run into in this section. Okay, but what I hopefully did is give you a good foundation from which to work, from which to problem solve, and think your way through some of the problems that you're going to encounter. Okay, if there's something you're totally stumped on, let me know. Okay, the other thing I'll also mention, the last two, the quadratic form equations, it doesn't just work with e to the x's. I can also have like a numerical base, like a 2 to the x or a 3 to the 2x, so on and so forth. Okay, we can have that way, and I could even have something where, you know, there's a coefficient other than 1 out in front of that lead term, right? So I could have like a 3e to the 2x, or for that matter, a 3 times 2 to the 2x. Okay, and then we have to factor by grouping, all right? So lots of things to take into consideration. There's a lot of things that could potentially happen here. Again, hopefully I gave you a good foundation from which to work. But by all means, when and if you have questions, shoot me an email, or see me in class tomorrow, and we'll make sure we get those questions answered. All right. Have a good night, and we're going to see you guys tomorrow.